Yeah, so last time that we started the collinearity. So just remember this slide. Okay. Yep. So suppose that we have the two predictors, x1 and x2, and the y is the response variable. So we say x as predictor and y is response, but this does not mean the cause and result, but just the x explains y. So x does not necessarily cause y, but just we say y as response and the x as predictor. And suppose that x1 and x2 are really similar variable. Maybe x1 is nearly equal to x2, or sometimes x1 is nearly equal to maybe -2 times x2. x1 is equal to -2 times x2. So anyway, so suppose x1 and x2 are linearly dependent. Then it's actually not feasible to identify this beta1 and beta2. Because if x1 and x2 are almost the same value, the 1.5 plus x1 plus x2 and 1.5 plus 2 times x1 are are the same. Okay, so if similar, then these two are the similar. So that means the coefficients are totally different, but the this entire quantity, quantities are almost the same. So we cannot really estimate the parameters. So that's the problem of multi-collinearity or just collinearity. So if we have more than two variables, the relationship may be more complicated. So not necessarily two variables are same, but at least one linear relationship between predictors. So basically, we cannot really identify the parameters efficiently. So that is basically the nature of linear regression. So we just minimize error. So that is our objective function. So if that is our objective, basically beta1 hat or beta2 hat are just a byproduct of minimizing errors. So we cannot really identify these parameters. And the last time that we discussed the one example, so we regress the balance of the consumers, the debt balance of consumers by age and the credit limit and credit rating. And the age and credit limit are both important variables to explain balance, and also the two variables are almost independent, so not related, age and limit. Also, the credit rating is important factor to determine the balance, but since limit and the rating are really closely related, almost the correlation coefficient of 1, so this regression model on the right-hand side may be problematic. And you can see that problem in this linear regression output. So if we see the coefficient of the credit limit, so the second model has much smaller coefficient, and also the standard error is much inflated. So we cannot really identify this standard error well. And that also indicates that the standard error for the coefficient of rating in model 2 isn't really good. It's pretty large. So as a result, we have really the small p-values in absolute values, and also the relatively large p-values, especially for limit. 0.0001 becomes 0.70. So it's much larger and becomes insignificant. Yeah, and the situation is like this. So we have estimated the standard error for beta hat. So that means that we are seeing just the one parameter at a time. So we are seeing just the width of this interval or width of this interval. This is what we have seen in the previous slide, the previous table. And you can see that the beta, so in the left pane, the beta hat is relatively small, but the right pane, the beta hat is relatively large. You can see the scale is different. So 0.16 to 0.19, that is actually 0.16, so that is around here to 19. So it's really tight, right? So, but in the right pane, so left pane, it's a pretty large, small interval, but the right pane, the interval is pretty large. But the fact is that actually really this beta hat limit and the beta hat rating have really the strong relationship. So actually in terms of this two-dimensional object, the uncertainty isn't really large. Uncertainty isn't really large, but if we think about just marginal distribution of beta hat limit, then that ranges from negative 0.2 to positive 0.2, so it's really wide. And we cannot even see whether beta hat sub limit is positive or negative. Yeah, but usually we only see, the one-dimensional information, just standard error of beta hat limit or standard error of beta hat rating. So it sounds very large, but the actual thing happening is the here and here. So two parameters are highly correlated. Yeah, that is what we have seen in the first slide. So if x1 and x2 are similar, we cannot really distinguish y is equal to 2x, x1, and y is equal to x1 plus x2, and y is equal to 2 times x2. If x1 and x2 are similar, we cannot distinguish these three. So 2, 0, 1, 1, 0, 2. So these are on a straight line, right? So so these parameters are hard to identify. And another way to express this phenomenon, the multi-collinearity, is calculating the variance inflation factor. So it's a kind of vague in the previous slide that the variance is inflated. Okay, if you compare this and this, then you can see. But okay, so just we think about the ratio of these two, and we call this as the variance inflation factor. So the variance of the standard error of the beta hat limit gets almost 13 times larger from here to here. So that is the variance inflation factor. So variance of beta hat. So maybe I should say the square of that. So the standard error is the square root of variance. So the variance of beta hat gets larger, then the ratio is called the variance inflation factor. How many times variance of beta hat j gets larger? And actually, there is a theorem that the variance inflation factor can be calculated as this right-hand side. And here, the right-hand side in the denominator, the r sub xj minus j is the multiple r square value when xj is regressed on other predictors. So that means that we regress xj on other predictors, the beta naught and the beta 1 x1 up to beta j minus 1, x j minus 1, and we exclude x sub j, then beta j. Maybe beta may not be the best letters to use. Maybe we can say gamma xj. We regress the beta j on these parameters. Maybe just to distinguish from original model. Maybe we use gamma j minus 1. So here j minus 1 and j plus 1 and up to the last one. So gamma p xp plus some error. So we can calculate multiple r square of this regression model. Then if we calculate 1 over 1 minus the r square sub xj given x minus j, then you can see we can prove that this is equal to this variance inflation factor. Yeah, we don't prove the theorem, but we use some matrix algebra to prove this. And here the x sub minus j means the x1 to xp, but excluding x j. So that we subtract xj as a set. Yeah, and okay, so there isn't specific the magic number to find the problematic regression, but if the variance inflation factor is more than 10, usually people think multicollinearity is severe. Okay, so basically we compare the model with the specific variable and the model with additional variables. Then we compare the standard errors. Then we can get the variance inflation factor. So in this case, actually the limit, so variance inflation factor, so standard error, in terms of standard error, this becomes 0.005 approximately to 0.063. So it becomes 12 times or 13 times larger. The variance is squared quantity, so even larger. So maybe 12 squared to 13 squared, so almost 150 times larger. So the variance inflation factor is the ratio between these two values. But we divide this by the standard error of the regression, the size of sigma. Yeah, so basically because the variance of beta hat is written as sigma squared times x transposed x inverse. X is the model matrix. So when we have the linear model in matrix form, y is equal to x beta plus epsilon, the variance of beta hat is written as this. And the sigma square is a nuisance parameter. So it's not our interest, but we have to estimate it. And you can imagine that if we think about the two regression model, we have maybe larger matrix, maybe x tilde, beta tilde plus epsilon, then variance of the beta tilde hat. This is equal to sigma square, the x tilde transposed x tilde inverse. So if we want to relate the ratio with the beta hat, we have to deal with this sigma. So if we want to prepare a simple formula, which is only determined by x or x tilde, this sigma have to be assumed to be the same. So that we have to adjust this sigma. So sigma is the standard error, residual standard error. You can see the residual standard error here and here. So we just standardize this size by sigma. Then if we standardize by sigma of each regression, then so this is the standardized one for the larger model, and this is smaller model. Then we get 12.67. And if we square this, then this is the variance inflation factor. And the variance inflation factor is actually calculated as this, the VIF function in R, and we can get the same value, 160.58. So, sorry, the variance or limits, so this one. So 160.59. So we have included the limit variable in both regression. So the ratio of these two is 160.59. So slight difference because of the rounding error, but the variance inflation factor can be calculated in this way. Yeah. So again, the variance inflation factor, we have two ways to calculate it. So one way is to calculate just the standard error of the beta j in two models and just compare it. and take square, then that is variance inflation factor. Another way is to calculate this 1/1 minus multiple r square of xj on other predictors. And we haven't proved this theorem, but both sides coincide always. Yeah, so in this case, the variance inflation factor is 160, and the VIF of more than 10. So that is 160 is much more than 10. So we say this as we have to at least the variance inflation is noticeable.
No.
Any questions? So you can
Sorry.
try the, yeah.
Sorry, Professor, I have a question.
Yep.
For measuring multicollinearity, can we
Yep.
use a correlation coefficient? For example, we can calculate the correlation coefficient tables, and if the correlations is more than, for example, 0.6 between two variables, then we can say that we have some sort of multicollinearity.
Yes, I can say, yeah, that's true. That's true. So we have, yeah, that makes sense. That makes sense. So we have basically, okay, so three quantities, y and x1 and x2. And yes, yeah, you can say that. Yeah, you can say that. Yes, yeah, can. Yeah, I think that's a similar concept. Yes, the x1 and x2 have the high correlation. Then that we can say that those are expected to have the large multicollinearity. Yeah, that's true. Yeah. Anyway, the variance inflation factor also is calculated by x only. It's not involved in y. So it does not involve y. So yes, I think those are similar concepts. Yeah.
Okay, thanks.
Yeah. Yeah. So just the variance inflation factor is more direct measure, right? So that you can see how much the variance was inflated. But yeah, basically that's the same. Yeah. Yeah, I think the difference is when we have the more predictors, x3 and x4 and so on, then yeah, so sometimes maybe x3 and x4 maybe changes the variance inflation of some specific variables. Right. So for example, most movement of y is explained by x3 and x4. Then even if x1 and x2 are highly correlated, probably it doesn't really matter. Anyway, correlation coefficient. Anyway, the beta hat are small, right? So in such a case, it's not really problematic, but yeah. So yeah. So the point is that the correlation between x1 and x2 only determined by x1 and x2. But in regression model, maybe we have other variables. In such a case, maybe depending on the relationship between other variables, x1, x2, and x3, x4, maybe variance inflation can be avoided, or can be avoided, can be maybe alleviated sometimes. Yeah, that's the only difference. But certainly, taking correlation that helps to understand the situation. Yes. Yep. So typically, for example, the economic variables, we have the multiple definition of employment rate, or multiple definitions to measure the output of the economy. For example, the industrial production, or GDP, or maybe the power usage or something. So those variables are similar. So in that sense, that we have to yeah, so combine variables sometimes. So we shouldn't use the too many similar variables sometimes. So in that case, the correlation coefficients are high, and then we have to avoid to use the all similar variables in one regression. Oh yeah, and this is just another way to calculate the correlation, the variance inflation factor in R. So just calculate the multiple R square and on of the limit on other predictors. Then we calculate 1 minus the R2, 1 over 1 minus R2. Then we can get the variance inflation factor. And how to resolve this issue? So the one intuitive one is to exclude similar predictors beforehand. So if we have the 3 definitions of unemployment rate to explain inflation rate, then you can just pick the most important unemployment measure, or just or maybe the average of 3 measures or something like that. So exclude similar predictors beforehand, or combine similar predictors beforehand. Combining the predictors, that we can use principal component analysis, or a little more advanced scheme, such as the state space models, which uses some the Bayesian statistics to summarize the multiple variables. And some method can choose, some variable selection method can choose a smaller number of variables, or it can drop some variables. So if we have 5 variables in the predictor set, some model selection criterion that drop the sum of many of them and just leave the most important predictors. So that is another way. And also, they ignore the issue. That is one solution. So in the sense that it doesn't matter. So we see that if x1 and x2 are similar, beta, maybe we have seen that the x1 plus x2 and x2 times x2 are similar. So it doesn't really matter much for the predicted value. So in terms of the estimated coefficients, it's a big change. 1 becomes 2 and 1 becomes 0. So, sorry, the other way around. So 1 becomes 2 and 1 becomes 0. So that's a huge change. But in terms of fitted value, it doesn't change much. So if we use the y hat, I mean the x1 plus x2 as y hat, or 2 times x2 as y hat. Anyway, so these two are very similar. So we can just ignore this issue, and we use the predicted value. And that is one solution. Of course, sometimes we have trouble. For example, suppose x1 and x2 have measurement error. Then the larger coefficient is problematic. Maybe 2 times x2 is still fine, but think about maybe 11 times x1 minus 9 times x2. Still, predicted values are similar between this and this model. But if x1 and x2 have some measurement error, so this quantity, 11x1 minus 9x2, have larger variability. So probably this is a better choice than this one. So in such a case, we have to think about it a little more. But the one simple remedy is just ignore the issue if your interest is just y hat. Yeah. But the bottom line is that the linear regression just focuses on minimizing error and not estimating parameters. So originally, identifying multiple parameters in one model is not easy in regression model, especially if you put many predictors, maybe 5 predictors or 10 predictors. Usually the coefficients are not significant because of variance inflation. Do you have any questions so far? Okay, so
Professor,
yeah,
sorry, I have another question about
sure.
multicollinearity. I
Mm-hmm.
think the big problem is we have prefect collinearity. For example, the
Mm-hmm.
exact relationship between variables. Because
Mm-hmm.
in all models, I think we have some sort of collinearity. Some of variables are always have some relationship together. But
Yeah.
the bigger problem is when we have just perfect collinearity. Am I true or not?
Oh, perfect collinearity. Yes, that's true. Yeah. So yeah, I think that we have two problems. So one is statistical problem, and one is the really mathematical problem. So so x1 and x2 are almost the same. Then we have the variance inflation. And that is what we discussed. And and another problem is that, yes, so we have perfect the relationship, such as x1 is equal to x2, or in case of three variables, possibly 1.5x1 plus 2.x2 is equal to maybe, I don't know, maybe negative 3 times x3. So that happens because of the definition of variables, right? So in this case, the beta hat is not estimable. Yeah, so that is a problem. So in this case, clearly you have to drop the some variables. Yeah, and of course there are some there are some other methods to estimate the parameters even when we have perfect linear relationship. And that is the regularization method. They're called such as rich regression, lasso, support vector machine, and so on. But so if we have perfect relationship, then we have to certainly remove some variables. That's true. So that happens when some variables are very scarce variables. For example, x1 and x2 are both indicator variables, and it have originally different meanings, but actually the data have the exactly the same values. So that's possible. For example, I don't know. For example, let's think about the housing data. X1 is indicator for the basement. So have the basement or not. And X2 is the variable indicating whether the house has the sump pump or something. And suppose all houses with basement have sump pump, then X1 and X2 become exactly the same variable. So in such a case, you have to drop one variable. So that's true. Yeah, and sometimes x1 plus x2 becomes x3 or something. Right? So for example, x1 is the number of hit the batter makes for the baseball data, and the x2 is the number of home runs or something, and the x3 is the number of total of hit and home run or something. So then we have x1 plus x2 becomes x3. So in such a case, clearly you have to drop the one variable to avoid the singularity. Yes, yeah, that's a good point. Yeah, that kind of problem often happens in the real data set. And even, for example, and also sometimes it happens when you divide the data set into several pieces. So you divide original data set into training set and a test set. Okay, so usually the data is originally cleaned in some way. So the original data set doesn't have any singularity, doesn't have perfect relationship between predictors. But suppose the original data set is divided into two parts, D1 and D2. D1 is training set and D2 is test set. And suppose test set is only 20% of the entire data set. Sometimes in D2, some variables are singular. So two variables are just the same, or maybe all values are 0 or something. So sometimes when you divide the data set into small parts, then this kind of singularity appears. Yeah, so yeah, that's important to mention. Yep. Yeah, thank you. Other comments? Okay, so now that we go to the section, the 3.c, so that is the qualitative predictors. So in short, the point is that for predictors, it does not matter even if it's a categorical variable. So if we have different type of y, the regression model should be totally changed, because even the simple linear regression, we have assumption in error term. If y is not continuous, for example, y is just the discrete variable with 5 levels, 1, 2, 3, 4, 5, then we cannot assume epsilon is normal. So we have to entirely change the model to justify the regression model. But the x, it does not matter. X is continuous, that's fine. If categorical, still that we can have a remedy for that. And this is the one example, the property cells and the number of bedrooms. This is the city of Troy data. And we have the 490 observations of 7 variables. And this is the date and the price and the style of the architecture, and the square footage, year, number of bedroom, and number of bathrooms. And the number of bedrooms, it's not entirely the continuous variable. In this data set, it can only take the value 0, 2, 3, 4, 5, 6. So there are no properties with the 1 bedroom in this data set, but that is either 0, 2, 3, 4, 5, or 6. Yeah, so it can be regarded as the qualitative variable also. Yeah, so we think about the situation. So basically, we have several ways to deal with this variable. So one is just to think this as numeric variable. So another way is to think about this as the categorical variable and prepare all dummy variables. So suppose the number of bedrooms are, okay, so 0, 2, 4, 0, 3 or something. Then we can prepare dummy variables. So just we think about the baseline, and we can exclude baseline. Suppose 0 is the baseline. Then we prepare the dummy variables for 2 bedroom, 3 bedroom, 4 bedroom, and 5 and 6 in the real data set. And we think about the dummy variables of this and this and this. So value is 1 only when the statement is true. So 2 bedrooms is true for only second observation. So only this observation is 1. Okay, maybe if we have one more line, then 1 again. And this is the dummy variable for 3 bedrooms. So only this one have the 3 bedrooms, so 1, and other elements are 0 and 4 here. Okay, and so we have the 2 ways to deal with the data. And now that we consider to compare the 2 models. So one is the simple model that the number of the bedrooms is regarded as quantitative variable. And the second model is maybe the number of bedrooms have nonlinear relationship with the price. So we have additional the variable here to represent the other factors. So basically, the number of bedrooms, the number itself is important as a numeric value, but possibly, we have a big difference between houses with 0 bedrooms and the houses with the 2 or more bedrooms. So to distinguish that kind of nonlinear relationship between the number of bedrooms and the price, that we add some dummy variables for each level. And we see that if these coefficients are significant or not. Yeah. So to be exact, okay, so to be exact, this is actually, okay, so the number of bedrooms, so that we have the indicator variable for the 2-bedroom. Indicator variable for bed is equal to 2. So we have maybe beta 5 plus this, and beta 6 times bed 3, and beta 7 times indicator variable, I mean dummy variable for bed is equal to 4, and the beta 8 times indicator variable of bed 5, and maybe indicator variable for 6 bedrooms. Okay, so we have this one. So I just say the beta sub 4i, but this actually represents the dummy variables. And okay, so think about it. That we have basically the 6 levels of I, the number of bedrooms, 0, 2, 3, 4, 5, 6. So except for the baseline, we have 5 variables. And we use 1 variable here. So actually we have only 4 additional variables. So if we have, we put 5, that is actually redundant. We have some linear relationship between beta 4 to beta 9. So we have to actually eliminate the 1 variable. So maybe we should remove the last one. Then basically we compare the first model with second model. The first model have 5 parameters, the beta 0, beta 1, beta 2, beta 3, beta 4. And the second model, we have the 5 plus 4, so 9 variables, beta 0 to beta 9. And we will see whether or not these additional variables have meaningful information in addition to the first model. Yeah. Okay, so the base model is here. We have the 4 variables. If we include intercept, 5 variables. And the second model is the bet as a factor. Okay, so as factor bet. Yeah. So we added the dummy variable for 2 bedrooms, 3 bedroom, 4 bedroom, 5 bedroom, and 6 bedrooms. Then, okay, so this is the result for the first model, the smaller one. And this bet is regarded as numeric variable or quantitative variable. Then coefficient is here. So 1 additional bedroom have actually the -8. So the negative $8,000 impact. Okay. So why this has negative sign? Do you have any explanation on this? So we regressed the price on square footage, year, number of bathrooms, and number of bedrooms. Larger house is more expensive. Newer house is more expensive. The more bathroom, more expensive. The more bedroom, more expensive. And in terms of that intuition, these 3 are reasonable. Square footage, 1 additional square feet, the $109. That's pretty reasonable. Year, 1 year newer than $778 more expensive. That's reasonable. Number of bathrooms plus 10,430. So 1 more bathrooms, about the $10,000. It's reasonable. Number of bedrooms, negative 8,000. It's a kind of counterintuitive. Why this happens?
Is it because obviously it's not is it because the bathrooms are so overpriced and it's kind of compensating for it, and it doesn't have to be logical if it's correct?
Yeah, you're right. So the point is that the square footage is already included. So the size of the house has already been adjusted. And still, if additional bathroom, so adding a bathroom costs a lot more. So that means that we have some, the positive, the value for the number of bathrooms. But think about it, so the houses with all bedrooms, we have no kitchen, no bathrooms, and just bedrooms. So 1,000 square feet house and just 4 bedrooms of 250 square feet each. Then that is pretty easy to build, right? So the no water and the the appliances. So it's actually much cheaper. So that's why. So
if if the rooms are also really small, since square footage is set, then people don't really like it either. So that could also be why the price would go down if you add more bedrooms to already a big square footage.
Yeah, that kind of preference also matters. That's true. So for example, 1,000 square feet house with the 4 bedrooms, people are fine with that. Maybe 4 too much, maybe 2 bedrooms, that's fine. If 5 bedrooms, even if walls, the cost some, maybe people don't like it. Yes, that's true. Yeah. Then it's cheaper. That's also another reason. But the main reason is that the square footage has already been accounted for. So given the fixed space, more bedrooms means a cheaper house. Yeah, you can see just the most expensive houses in Bloomfield Hills, maybe 8,000 square feet or 10,000 square feet. Still, they have only 5 or 6 bedrooms. Sometimes they have 10 bathrooms. So so the thinking about that kind of reasons is helpful when you practically do regression for the real data. So it's really harder to interpret the result when we have the more predictors. Still, it's manageable in this case, but I live in Troy, and I just looked at the property tax. The property tax is determined by these ones, and I believe that they use some regression model. And if the houses are close to the major highway or the major roads, then the tax is lower. But sometimes the major roads that don't have much traffic, so even such a case, the property tax is much lower. So actually, if you carefully pick up some houses, then you can save some money on the tax. So this kind of regression model is useful for to determine, for example, tax assessment. Okay, so this is the second regression model. So this is a larger model. So we don't assume linear relationship between the number of bedrooms and the number of bathrooms. And actually, we see the result here. And this is a redundant predictor, right? So we have basically 5 parameters at maximum, and we include 1 quantitative variable. So we can include only 4 additional dummy variables or indicator variables. So the last one is simply redundant. Then actually these values are significant, statistically significant. So that means adding these predictors are useful in addition to the number of bedrooms. So, okay, so think about the impact of the number of bedrooms on the price. So these are the baseline based on square footage, year, bathroom, and the intercept. This is pretty stable. Even we added these variables, these don't change much. Maybe intercept changed. So the number of bedrooms, we have the 0, maybe 0, 2, 3, 4, 5, 6. And the baseline, okay, so maybe we have to distinguish color. So the baseline is the negative 31,000 per bedroom. So that means 0 bedroom. Okay, so at first the quantitative variable negative 31K. So 0 is 0, 0, 0, 0. And the 2 bedrooms, the negative 62K, 62,000. Negative 3, 93,000, and negative 4, I mean 4 bedrooms, the 124,000 negative. 5 bedrooms, 155. The 6 bedroom, 186. Then we have to consider these values. 2 bedrooms, the plus 83. So the positive 83. So 0 is 0. And 3 bedrooms, this is the plus the 109, plus 109. And number of 4 bedrooms, then 125. And the 5 bedrooms, that is the plus 168, 169. And 6 bedrooms, so this is actually we cannot evaluate it. So the number of bedrooms, the total impact of the bedrooms, this is 0. This is negative 62 plus 83, so positive 21K. And this is positive 16, so 16,000, and a positive 1. And this is positive 14. And this is strange, but the 6 bedrooms that we don't have any value, so negative 186. So this is the total impact. So yeah, this model is a little bit strange. So basically the number of bedrooms should be between 2 and 5. Yeah, that's reasonable because the too many bedrooms, it doesn't add value. Yeah, probably maybe this is a kind of exceptional case, maybe only 1 or 2 houses. So that's why that we have very unstable result. But this is the case. So actually, in the previous page, the 1 additional bedroom, just the negative $8,000 impact. But the actually number of 2 bedrooms, 3 bedrooms, 4 and 5, it doesn't change much.
Why isn't 0 bedrooms minus 31K? Because I would assume if you have a 0 bedroom house, the price would go down a lot.
Sorry?
Like if you have a 0 bedroom house that you try to sell, why isn't that minus 31K for the total?
Oh, this is the number of bedrooms. Okay, so number of bedrooms times negative 31. So negative $31,000 for each additional bedroom. So
sorry.
Okay, so this green one is quantitative variable. This is the numeric variable. So this means the number of bedrooms. And the others are indicator variables. So when the number of bedrooms is exactly equal to 2, we have to add 83,000, maybe 84,000. This is indicator variable. Okay, so the 0 bedrooms, then we have to multiply 0 with negative 31, that is 0. Then we don't have any indicator variable for 0 bedrooms, so do nothing. So the total is 0. If the 3 bedrooms, then number of bedroom is 3. So 3 times negative 31, so negative 93. And if the house exactly has 3 bedrooms, we have to adjust the 109, positive 109,000. So plus 109. So the total impact of the bedroom is the negative 93 plus 109, so positive 16. Yeah, so this is how to read this output. Yeah, so actually this indicates that the number of bedrooms should be between 2 and 5 to have a better price. I mean, higher price. But in total, the relationship between the number of bedrooms and the price is not linear. So that's why that we have the significant p-values here. So practically, the implication is that the number of bedrooms between 2 and 5 bedrooms have significantly higher price than houses with 0 bedroom or 6 bedrooms. Yeah, so the above result indicates when we introduce a parameter for each level of the number of bedrooms, many of them are significant predictor of price. Yeah, but we have to be a little bit careful because this really depends on the baseline. So we can say that the 2-bed, 3-bed, 4-bed, 5-bed, these are significantly different from the 0 bedrooms, but it doesn't say anything about, for example, difference between 4 bedrooms and 3 bedrooms. Maybe difference isn't really large. That's possible. So in this case, the difference is only maybe 16,000. So maybe significant, but maybe not significant. So we don't really know. So these are, compared to the baseline, right? So compared to the baseline. So yeah, that's the case. And actually, if we drop this quantitative variable, the number of bed, if we drop this one and we fit the price on square footage and year and the number of bathroom and the just factor variable, the bet f, then actually I think the default in R is that we think about just the linear term first. I think the bet L or bet 1, I forgot what's the name, but at first I'll check the linear term. Then after that, I'll check the quadratic term, so bet Q or something, quadratic term. Then the third, we check the cubic term and so on. So basically, the R assumes the number of bet and price, the relationship. At least we think about the linear function. Then next, the quadratic function. And the next cubic function and so on. And probably they use a different base because in this case, the cubic curve and the quadratic curve are really similar. So probably R standardize it to make it as maybe probably the linear term and probably the cubic, I don't know, maybe the cubic as this and maybe the quadratic as this and the cubic as maybe different one. Cubic as, I don't know, but maybe like this. So they distinguish the 3 curves more efficiently. So if we have 1, 2, 3, 4, 5, 6, well, we have 7, but yeah, like this. So you can see at first the linear term is the significant or not, then quadratic term is what, and cubic term, and so on. And this is the Anova table to see whether additional predictor that helps to improve the model. Now, for example, let's see the number of bathrooms. Okay, so suppose that the price is explained by square footage and year. If we add another predictor, but the number of bathrooms, does it have a significant impact on the model or not? And this p-value indicates that the bathroom has a significant predictor. So this basically is obtained by comparing this contribution to lower the error size. Yep. So sum of squares. So if we have all of these predictors, the residual size is here. And these predictors, each additional predictor has this impact to lower this number. And after we divide this by the number of parameters, actually only one parameter here, so one here. So residuals, this is the n minus number of parameters. We have 8 parameters in here, so n minus 8. And we divide by this number by n minus p, 481. Then we take the ratio. Then this f value follows f distribution with df1, 481. And based on this, we can calculate the p-value. So this means the number of bathroom has significant contribution to improve the prediction, even we have already accounted for square footage and year. And if we add the number of bedroom of the quantitative variable, still it has positive impact. And bet as a factor variable, still has impact. So all variables have the significant predictors here. So here we can clearly see if we think about the number of bedroom as a factor variables, so that means that we assume the nonlinear relationship between price and the number of bedrooms, it is helpful to improve the model. And AIC, AIC also measures how good the model is for out of sample performance. So if we have a new data set, then how good the model is. So AIC is a measure for the test performance. And we compare two models, the model with only the number of bedrooms as linear term and the number of bedrooms as a factor variable, nonlinear term. And we have the AIC of 11,797 and 11,779. And remember that AIC is negative 2 times log likelihood of the model plus some term. So anyone remembers what is AIC? Akaike information criterion. So AIC balances between the fit of the model and the size of the model. So simpler model is better, but the better fit is better. If we have a really large model, then we can make error size smaller, but that model is too complicated. So probably for new data set, it does not really work well. And the log likelihood, this is the fit of the model. So AIC, the smaller AIC is better. And better fit means the better log likelihood, so smaller AIC. So that is fine. And then we have to make a simpler model. So we have to penalize a large model. So do you remember what term is in the AIC here? How many of you have already studied AIC somewhere? Maybe.
I learned it a bit in time series.
Okay.
I learned it in 5030.
Yeah, 5030 that we dealt with it. The 5800 may not cover that. Anyone have taken 5800 in these years? Okay.
Yeah, I did, and we did not cover it. No.
Did not. Okay, I see. And the AIC is the negative 2 times log likelihood plus the 2 times number of parameters. So P is the number of parameters. If y is equal to beta naught plus beta 1 x plus epsilon, we have 2 parameters, beta naught and beta 1. So large model, we have large P. So we penalize it. So we add 2P. So if P is larger, AIC gets larger. So that means AIC gets worse. Yeah, and the model 3 and model 4. The model 4 has the AIC, actually 18 smaller AIC than the model 3. So what's the meaning of 18? So penalty is 2 times P. So if we add 1 variable for nothing, then AIC gets worse by 2. If AIC doesn't change, then okay, we added some variable, but at the same time, log likelihood gets 2 smaller, 1 smaller. So negative 2 times log likelihood get 2 smaller. So the 2 is kind of the baseline. So 18 is pretty large number. 18 corresponds to 9 variables, 9 meaningless variables. So actually the AIC, we added 4 variables, but the AIC doesn't get worse, but it gets better by 18. So that we can safely say the model 4 is better. If AIC is similar, then additional variable, the contribution of additional variable is questionable. And AIC gets larger, then probably model gets worse. If AIC gets larger by almost 2, then probably that variable predictor is garbage. Yeah, and the same analysis can be done for bathrooms, but we don't do that here. Yeah. And okay, so do you have questions? So overall, anyway, the larger model is better in this example. So in terms of AIC, the larger model, model 4 is better. And in terms of ANOVA, the model 4 is better. And in terms of the just linear regression output, the many coefficients are significant. So we should include these variables. So the number of bedroom and price are don't have linear relationship. It have non-linear relationship. To be exact, the 2 to 5 bedrooms are optimal for this market. Yeah, I think in 1950 or 60, there was a survey that the United States have shortage of the apartments with 3 bedrooms because and one reason is that some older survey, they said that the 2-bedroom apartment is the most popular. So that's why the people built too many 2-bedroom apartments. So then actually the supply exceeds the demand, and actually the supply of 3-bedroom apartments are too small. And later the 3-bedroom apartment have some premium. So this kind of analysis may be useful and interesting. Yeah, and this is data science course. So we don't stick with the linear assumption between variables. So linear model can deal with this kind of model, but sometimes this model, so-called interaction term, has the significant impact. Yeah, for example, this one. So the sales and advertisement on TV and radio. And both have positive coefficient. So more advertisement on TV is good, more advertisement on radio is good. But if we do both, actually that also have positive effect. So so if we spend the $1 million more on TV, then the sales goes up by some amount. And the 1 million on radio also increase their sales, but we have interaction. So if we do both, the sales increase more than linearly. So maybe if people watch the same product on both TV and radio, then more people buy that product. Yeah, so that kind of analysis is good. And the engineering insight is that this kind of interaction term matters. So if we have 3 variables, we have so many possible interaction terms. The x1, x2, x3 are linear term. And we have interaction term x1, x2, x2, x3, x1, x3. And also we can think about the quadratic term, x1 square and x2 square, x3 square. Also maybe x1, x2, x3, or x1 cube, or x1 square, x2, and so on. But usually higher order terms are not that significant. So probably the quadratic terms, these are often significant, but the cubic terms are even higher terms. Usually they're not significant. If we think about x1 times x2 square times x3, probably that term isn't significant. So we start with the smaller one and it gets larger and larger. So that is usually a good way. Yeah, so there are some examples in which we can expect the interaction. So for example, the crop yield may be affected by the amount of the fertilizer only when sunlight is not enough. Or southpaws pitch well only when the batter is left-handed. So this is also another interaction. It's not that southpaw is always better or so right-handed batters are better, but if we combine, if we think about the match between southpaws and the left-handed batters, then the pitchers have advantages. Yeah, so you can include the interaction terms. Yeah, especially in the past, some students do the final project on the data set, which includes the longitude and latitude of some the houses or some other data. And longitude and latitude, so originally it has some geometric meaning. Suppose these are the location of houses. And suppose here is the train station. Then you can see these houses have more expensive than these houses. So in that case, actually, we think about the distance between the some point. Maybe I would say the AB, and this is x1, x2. So naturally, the x1 minus a square plus x2 minus xb square, this matters, right? So the quadratic term, the x1 square, x2 square, is meaningful predictors. And in some cases, this is not just circle, but the ellipse. Geographic location that isn't necessarily represents the time needed to reach to some point. So if contour is like this, then it's certainly meaningful to include x1 times x2 as a predictor. So often the quadratic terms and the interaction term, second order interaction terms, are useful for the geographic reasons, by geographic reasons. Okay, so now yeah. Do you have any questions so far? Interactions? So of course, if you have many variables, you cannot include too many interactions. If you have 100 variables, then the 100 variables, then quadratic terms have 100 terms, and the interactions, we have maybe 4,500 interactions. So if you have many predictors, we cannot include all interactions. So we have to compromise at some point. If we have a smaller number of predictors, then we can include more interactions. But of course, we ignore other predictors. So we have pros and cons. Okay, so now the k-nearest neighborhood. So in chapter 2, that we introduced the nearest neighborhood method for categorical problem, so the classification problem. But here, the linear regression, also that we can use the k-nearest neighborhood. So sometimes the k closest observations to, in terms of x value, they can determine the predicted value at that specific x. Okay, so let's think about that. We have the data x1, y1. x1 may be the multidimensional. Maybe if 3 variables, maybe x1 is in R3. Then we have data set x100, y100. Then we have new observations. One new observation, maybe x naught, and y is unknown. Then how to predict y naught? We choose maybe 10 closest observations out of these 2x0. Then take average value of y. So that is a pretty data-oriented way to make a guess on y naught. And number of observations, here I said the 10 observation we choose, but how to choose that neighborhood, that really depends. So basically, we have to choose the number of observations, or we have to set this neighborhood in some way. Maybe distance between x0 and xi is less than 1, or something like that. So we need some criterion to choose how many observations or what kind of neighborhood to use. But anyway, so if we take average of this, then this is pretty flexible scheme to estimate the y naught. And this is the one example. So x1 is here, x2 is here, y value is here. And okay, so we have observation. Orange dots are observations. So we have maybe about 100 observations, maybe 50, about 50. Then this surface, the red, green to blue surface. So this is the fitted surface. So given the value of x1 and x2, that we can get some point, then this point is the predicted value for y. Okay, so we have x1 value and x2 value, then predicted value is here. And of course, here the case 9, so the 9 closest observation doesn't change if the point only moves a little bit. Right? So we only have 50 observations in total in the beginning. So that's why this is not the smooth curve, but flat in some area. Within this area, the nearest 9 observations are exactly the same. And if we have the larger k, I'm not sure what is k, but oh, sorry, this is k is equal to 1. K is equal to 1. One observation, one closest observation. And if we take the more observations, then the surface becomes smoother. Because the point that moves a little bit, maybe only 1 out of these 9 closest observations changes. So the only slight difference in the fitted value y. So large k, smoother. Smaller k, bumpy. But large k, smoother, but the larger bias in some cases. It doesn't adjust to the data too. Yeah, so this is the chapter 3. Okay, so that's it's 8:15. But do you have any questions on k-nearest neighborhood method or the chapter 3 in general? So after chapter 3, the lab session, the R code session, probably I will give out the first homework to do some regression analysis.